Hello everyone, this is lesson D4, energy in simple harmonic motion. If we remember, first of all, kinetic energy is just the energy stored within the motion. Right, so if an object is moving, it has energy stored within it, and that energy is kinetic energies, or that store is what we call the kinetic energy store. And that store has the equation 1/2 mv squared. The potential energy is energy stored within the position. And within a spring, what that's referring to is the position in reference to the equilibrium position, how much it's been deformed or stretched. And so that potential store has a formula of 1/2 kx squared. Now, taking a look at the law of conservation of energy, this says that energy cannot be created nor destroyed. Which means that the energy that we have before is equal to the energy that we have after. And for purposes of what we're doing, we're just going to be looking at the kinetic and potential energies. Now, I do know, or you probably do remember, that some of this is also work done to friction. And so this is usually lost in a thermal store. However, what we're going to kind of just take a look at the ideal scenario, or the frictionless scenario, as we run through this. So taking a look at what's happening with the energies as things move in simple harmonic motion. You may remember this video where an object, as it moves back and forth, we see changes in acceleration and changes in velocity. And so at the equilibrium position is where we will see the maximum amount of velocities, the least amount of force, because we've got the least amount of displacement, or the least amount of acceleration, I should say, according to the graph. And when we reach the amplitude, that's when we've got the largest displacement, and therefore the largest acceleration, and therefore the lowest velocity. What we're going to do is translate that into energy. And so at this point here, as it's vibrating back and forth one complete cycle from amplitude to amplitude, now this is horizontal, not vertical, but it's the same idea. Here this is at the amplitude, so potential energy will be at a maximum. The direction of the force, or the restoring force on us, will be to the right. The velocity will be basically zero, and the kinetic energy therefore will be at a minimum. Now here it's in between, so we're going to put other, right? Other. The direction of the force is still going this way, but the velocity is increasing to the right. And so kinetic energy, therefore, is also going to be increasing until we reach the equilibrium position. Potential energy is at a minimum. There is no force now acting upon this object. It's now back to its regular position. Velocity is at a maximum to the right, and the kinetic energy, therefore, is at a maximum. We get to this other position as it continues moving along. So what we see here is the potential energy is increasing. The direction of the force is now acting to the left. The velocity is decreasing, but it is still moving to the right. And kinetic energy is therefore decreasing as it's slowing down until we reach the amplitude, where potential energy is now going to be at a maximum. The force is all the way here. The velocity is 0. And the kinetic energy, therefore, will also be 0, or minimum. As we head back down, the potential energy is going to be decreasing. The force is still acting towards the left, where the velocity is now increasing to the left, and so we're going to see an increase in kinetic energy until we get back to that equilibrium, where potential energy is 0. There is no force acting on because there is no displacement. We're going to see a maximum velocity, but now we're heading to the left. And the kinetic energy is at a maximum. All right, until we reach this, again, this other spot where we're going to see the potential energy increasing. The force is now acting to the right, where we will see a decrease in the velocity even though it's moving to the right, and so therefore the kinetic energy is totally decreasing until we reach back to where we were before, where we're at a maximum here. Force is this way, 0, and we'll put a 0 in. So that's kind of the chart of what's happening within a full cycle in terms of the energy and the velocity and the kinetic energy. Kinetic energy runs the same as the velocity, or runs with the velocity, and potential energy runs along with the displacement. Key thing here, though, is that there is no direction on energy. And that is because energy is what we call a scalar quantity. It has magnitude, but not direction. Okay, so example number 1, we've got a 2 kilogram mass attached to a 50 Newton per meter spring. The mass is displaced 45 centimeters or 0.45 meters from the equilibrium and then released. So if that is the spot where it is pushed to and then released, as it moves back and forth, this will in fact be the amplitude. Okay, so 0.45 is the amplitude. What is the potential energy before the spring is released? Well, that's going to be using the 1/2 kx squared formula. So 1/2 of 50 times 0.45 squared. And you're going to find that's 5.06 joules to 3 significant digits, or to proper 2 significant digits, 5.1 joules. What happens to the potential energy once it's released? Well, it's going to take a mechanical pathway to become a kinetic store. Now, that mechanical pathway is the force that is acting upon this from the spring. As it starts to move. Now, if we want to calculate the maximum velocity, that maximum velocity is going to happen at the equilibrium. And if we want to calculate that maximum velocity, we need to remember that all the energy that we had at the amplitude is going to be equal to the energy that we have at the equilibrium. And so at the amplitude, we only had potential energy, and we calculated that to be 5.06 joules. We really should be keeping our calculator answer from part A here. And at the equilibrium, it's all kinetic energy. Okay, so we're going to finish plugging in those numbers. And as we solve for V, 1/2 and 2 becomes just 1. So it's essentially cancel themselves out. Square rooting that, you wind up with 2.3 meters per second as being the maximum velocity to 2 significant digits. Now, this maximum acceleration is going to happen at the amplitude. That is where we have the maximum displacement and therefore the maximum amount of force. Remember, the force is equal to negative kx, which is Hooke's law. Now, we're not worried about which side it is, whether it's up or down, so we're just going to worry about the absolute values. And so ma is equal to kx. Okay, again, no direction is going to be given within this question. So the mass here is 2 kilograms. 50. I'm looking ahead. The K value is 50, and that maximum acceleration again happens at the amplitude, which is why we put the 0.45 here. And when you solve for that acceleration, you're going to get 5.6 meters per second squared at the amplitude. Again, to 2 significant digits. Taking a look at this last example, 2 points along here, the energy at the equilibrium is equal to the energy at the amplitude, which means 1/2 mv squared is going to be equal to 1/2 kx squared, where that x is representing the displacement at the amplitude. We've got this spring, it's vibrating back and forth. We want to know what the maximum displacement is, which we've labeled here x. Sometimes it's a, we're keeping it as x though. If the maximum speed, what we have at the equilibrium, is 0.12 meters per second. Now, if you multiply both sides by 2, you'll notice that the 1/2s really cancel right out of this. So 0.2 times 0.12 squared is equal to 15 and x squared. That's what we're looking for. Dividing both sides by 15, and then we'll square root it. Don't forget to square the 0.12 as you're calculating. You're going to wind up with 0.014 meters for x, or 1.4 centimeters for x. So this is vibrating back and forth over a very short amount of time. There's only 2.8 centimeters, 1.4 either direction, in terms of the distance as it's vibrating back and forth. Now let's just, for curiosity's sake, this is not part of the question, but for curiosity's sake, let's just take a look at what the period of that would be, because that is m over k, the mass being 0.20 kilograms, the k value being 15. When you calculate this out, you wind up with 0.73 seconds, which does make sense. If this is only going a little bit, this is actually going to be vibrating pretty quick here. Okay, hope that helps. Thanks for watching.